Hello! In this video, I'd like to talk about my other favorite esoteric programming language, Diophantine Equations. A Diophantine equation is a polynomial equation where we're asking if some polynomial is equal to 0. In particular, we're looking at multivariable polynomials and focusing on when the solutions are exclusively integers. Hilbert's 10th problem asks if there is some general algorithm for solving these, some computer program that we can feed a polynomial into, and it will definitely tell us if there is a solution or not. It's worth noting that the single variable case isn't very interesting. The rational root theorem gives us a set of possible roots to check, and that's it. In the case where we're trying to figure out if there are complex solutions, even if we're working with multivariable polynomials, it's actually not that bad. Complex numbers are all about polynomials having roots. The real number case, on the other hand, is trickier, but there are algorithms for determining if there are roots, and I've made a video discussing some of the techniques involved in this. On the other hand, determining if a system of multivariable polynomials has integer solutions is much harder. There is no general algorithm because if there was, we could use it to solve the halting problem. This is highly counterintuitive, that as we restrict our attention from the complex numbers to the real numbers to the integers, the problem of solving polynomial equations actually gets harder. But a good way to think about this is that looking for integer solutions requires us to, in addition to determining if there are real solutions, determine if those solutions are integers. So we're doing a little bit more here. Just as when we're restricting from complex solutions to real solutions, we have to not just determine if there are complex solutions, but also if those solutions that we found are real. So again, we're doing just a little bit more. And that little bit more makes the problem harder. So in this video, I hope to show you why Diophantine equations are so difficult to work with, how we can translate any computer program into an equivalent Diophantine equation. We'll start off by expanding the problem without changing its difficulty. It'll be really convenient to work not with equations of the form some polynomial equals 0, but some polynomial equals some other polynomial. And of course this is equivalent, we're just looking at when the difference of those two polynomials is equal to 0. We also might be interested in solving a system of polynomial equations, finding values of x1 through xn that simultaneously satisfy a collection of polynomial equations. In this case, we can transform our system of polynomial equations into a single polynomial equation. We know that f1 through fn are equal to 0 if and only if the sum of their squares is 0. If our x1 through xn make any of the polynomials non-zero, that adds a positive term to this sum, and none of the other terms can cancel it out since they're all non-negative. So, for instance, suppose we're interested in finding out if there's an x and y whose sum of squares is a square and whose sum of cubes is a cube. We first subtract the right-hand side from both equations to get two equations of the form some polynomial is equal to 0. Then we square both polynomials and take their sum to get a single equivalent some polynomial equals 0 type equation, the type of equation that we were originally interested in. And so really, Hilbert's 10th problem is about systems of polynomial equations, and we just have to show that we can translate an arbitrary computer program into an equivalent system of polynomial equations. One might wonder, what if we dropped even further down to the natural numbers? Is it even harder to tell if a polynomial equation or system of polynomial equations has natural number solutions? The answer is no, and we can show this using a neat number theoretic result. Every natural number can be written as the sum of 4 squares of natural numbers. This is fairly simple to prove, but I won't prove this result in this video. I'll link to some proofs in the description. As such, we can add in a new equation to any system of polynomial equations to require that a variable be non-negative. First, create new variables, let's say a, b, c, and d, and then require that xi be the sum of their squares. And in fact, if we wanted to, we could require all our variables to be non-negative by having one of these for each of them. And so it actually winds up being equivalent, either having an algorithm for solving whether a Diophantine equation has integer solutions or whether a Diophantine equation has natural number solutions. Suppose that we had an algorithm for solving if there were integer solutions to a Diophantine equation, and we wanted to determine if a Diophantine equation had natural number solutions. So let's say we wanted to determine if x squared minus 3y squared equals 1 had any natural number solutions. If we consider our natural number Diophantine equation as an integer Diophantine equation, we're going to want to add on some extra 4-square constraints in order to force x and y to be natural numbers. And again, because any natural number can be written as the sum of 4 squares, these extra equations won't place any extra constraints on our x and y. Then we'll use our algorithm for determining if there are integer solutions to this Diophantine system. Again, we'll convert this system into a single equation, run that through our algorithm to get some sort of solution. Note that the extra variables a through h could be negative, but we don't care about them and we're squaring them, so it doesn't really make a difference. What we do care about is the values of x and y, and they must be non-negative in order to satisfy our 4-square equations. So they're the solutions that we're looking for our original equation. This shows that a tool for determining if there are integer solutions to Diophantine equations is at least as powerful as a tool for solving natural number Diophantine equations. And we can do the reverse to show that they're equivalent. So suppose that we had a Diophantine equation and we'd like to tell if it has integer solutions. So same equation here, but now we're allowing x and y to potentially be negative. And now we want to imagine that instead of having a tool for solving integer Diophantine equations, we have a tool for determining if Diophantine equations have natural number solutions. So we're going to take our integer Diophantine equation and translate it into the following natural number Diophantine equation. We're going to replace each variable by a difference of 2 variables. As our x and a and y and b take on arbitrary natural number values, the difference is going to take on arbitrary integer values. So if we can find some sort of natural number solution to this equation, those differences, x minus a and y minus b, are going to give us the original integer values for x and y that we were looking for. So really, determining if Diophantine equations have natural number solutions and determining if Diophantine equations have integer solutions are the same difficulty of problem. And here I've been a little bit loose about whether we're hunting for solutions or just trying to determine if there are solutions. Those are also equivalent. If we know there's a solution out there, we can go hunting for it. And if we know the solution, then we know that a solution exists. In light of the equivalence of determining if Diophantine equations have natural number solutions and determining if they have integer solutions, I'm actually going to want to focus on natural number Diophantine equations for the rest of this video. The coefficients of the polynomials I'll still allow to be integers, but the solutions, I'm just going to focus on the solutions being natural numbers. Let's continue on this process of adding to our language without increasing its power, of adding new tools or things that we can say, all the while maintaining our ability to translate back to a single Diophantine equation. Specifically, suppose we wanted to express an inequality that we're looking to see if there's some values of x and y that make some polynomial f of x strictly less than some polynomial g of xy. Well, we can translate this sort of assertion into a polynomial equation, add in a new variable z, and then assert that f of xy plus z plus 1 is equal to g of xy. Remember that we've switched to requiring that our variables be natural numbers. If we want to do something like this over the integers, we'd need to use the four squares theorem and say something like f of xy plus a squared plus b squared plus c squared plus d squared plus 1 is equal to g of xy. If we wanted a less than or equal to, we could just get rid of the plus 1. We can also add in modular equivalences. Suppose we wanted to check if there's some value of x, and maybe some other variables too, that make f of x congruent to g of x modulo h of x when we plug into those polynomials. Well, we can translate this to an assertion that f of x minus g of x is some multiple of h of x. Well, okay, really we need to say that f of x minus g of x is some integer multiple of h of x. So since we're restricting our variables to be natural numbers, we need to say that f of x minus g of x is equal to a minus b times h of x for some a and some b. Let's take a look at this in action. Suppose we're interested in solving this system here. X squared plus y squared equals 100, x is less than or equal to 2y, and x squared is congruent to 5 modulo y. This is a system of equalities, inequalities, and modular congruences, but we can convert it to a single polynomial equation, first by translating it to a system of polynomial equations. Again, x is less than or equal to 2y will translate to x plus a is equal to 2y, and x squared is congruent to 5 modulo y is going to translate to x squared minus 5 is equal to b minus c times y. And then we can use our procedure for translating systems of polynomial equations to a single equation from before. So again, being able to toss in these extra sorts of constraints doesn't really change the difficulty of the problem, doesn't really change the expressiveness of Diophantine equations. It just makes it easier to talk about certain things using them. It's worth taking a moment to formalize what sorts of constraints we can add into our systems without increasing the difficulty of solving them. I'll call a relation phi on variables x1 through xn Diophantine if it is of the form there exists some y1 through ym so that the x's and y's satisfy some Diophantine equation. Right, we can rewrite the relation x is less than or equal to 2y as there exists an a such that x plus a is equal to 2y. Or x squared is congruent to 5 modulo y as there exists b and c such that x squared minus 5 is equal to b minus c times y. And this is what allowed us to toss in these sorts of constraints into our systems. And there's lots of different ways of looking at these things. We can think of them as projections of the set of solutions to our polynomial equations. Right, we're looking at the set of all x1 through xn and y1 through ym satisfying some equations, and then ignoring the y's and just looking at the x's. Or there's a very nice logical perspective here. These relations are all given by formulas in the language of the natural numbers with addition, multiplication, equality, there exists, and or. That is, first-order logical formulas that don't have for all or negation in them. And actually, arbitrary negation is an issue only because it can turn existential quantifiers into universal for all quantifiers. We can negate specific equalities with a is strictly less than or is strictly greater than sort of situation. There's a little bit extra that you have to prove here, specifically given two polynomials f and g, that you can find a polynomial h that's equal to 0 exactly when one of f or g is equal to 0, but I'll let you prove that on your own. And ultimately, it will turn out that any predicate is Diophantine if and only if it is given by some computer program. And this is where the whole undecidability business will come from. In my video on Lucas sequences, I proved that exponentiation is Diophantine, that you can rewrite the equation t is equal to k to the n as there exist solutions to some giant system of polynomial equations. Note that there's further expansion you have to do, rewriting the modular congruences and inequalities that we have here as polynomial equations, and there's also some simplification that you can do here. This is profoundly surprising, and for a long time it was conjectured to be impossible. But this result opens up a bunch of brand new possibilities for what we can do with Diophantine equations. For instance, we can take the equation of Fermat's last theorem and break it apart as a system of equations. A plus b equals c, a is equal to x to the n, b is equal to y to the n, and c is equal to z to the n. And then rewrite those last three using the giant system from the last slide. And we'll have a bunch of separate variables for each of the three equations. Here we're creating new variables to represent the sub-expressions of our original expression, and creating lots of equations to describe how these sub-expressions are related to each other. This process is called relationalization, and it's very handy. It allows us to take Diophantine functions, Diophantine relations that are functions, and use them as part of our equations. Now, hopefully you see here that we're already in a bit of trouble if we had hopes for an algorithm for solving Diophantine equations. If we toss in some inequalities on x, y, z, and n, we get a system that has a solution if and only if there's a non-trivial counterexample to Fermat's last theorem. If we could then pop that into an algorithm for solving Diophantine equations, it would resolve Fermat's last theorem. It would either find a solution to our giant Diophantine equation, in which case we would have a counterexample to Fermat's last theorem, or it could tell us that there is no solution, and then Fermat's last theorem would be true. So intuitively, if we had an algorithm for solving Diophantine equations, running it and proving it correct is at least as hard as solving Fermat's last theorem. And you can do this sort of argument with a number of other really difficult math problems. Some of them might even be open math problems. In many cases, when we're talking about nesting of functions, it's useful to break apart those nestings using relationalization. For instance, we can view a polynomial in terms of compositions of addition and multiplication applied to some basic atoms. And as we discover more Diophantine functions, we can view those as part of our compositions too. Suppose we have a polynomial equation like x squared minus 4xy plus y squared is equal to 1. We can establish a new variable to represent each sub-expression of our polynomial to get a system of much simpler polynomial equations. For instance, we can establish a new variable a to represent x squared. This lets us simplify our equation down to a minus 4xy plus y squared is equal to 1, as long as we add in another equation, a is equal to x squared. This isn't much of a simplification, but if we keep doing this, eventually everything will become very simple. So next we replace xy with b and add in the equation b is equal to xy. And then we replace our 4b with c and add in the equation c is equal to 4b. Next we replace d with y squared. So now our original equation has simplified down to a minus c plus d is equal to 1. Provided all of these other equations on a, b, c, and d hold. Next, we can replace a minus c with e to get e plus d is equal to 1. And finally, we can replace e plus d with f, which gives us the equation in the end, f is equal to 1. So we've turned the question of whether there's a solution to our original single complicated equation to whether there's a solution to this large system of really simple equations. And the different sorts of equations have pros and cons to them. The big downside to having this giant system is, of course, that we have lots and lots more variables to deal with, and often that's a deal breaker. But something neat happens if we translate this system back down to a single Diophantine equation. Right? We take the differences of the left and right-hand side of each equation and We square them and we add them together, and we are asking when that's equal to 0. And what's interesting about this new Diophantine equation is that, so it's equivalent to the original one, and it only has degree 4. Each of the small polynomials we get when we take the differences is of degree at most 2, and then when we take the sum of squares and set that equal to 0, we get a polynomial equation of degree at most 4. So every Diophantine equation can be rewritten as an equivalent Diophantine equation of degree at most 4. So that's kind of interesting. All of the difficulty happens already at degree 4, provided that we're allowed to have lots and lots of variables. One of the things that we can use our ability to talk about exponentiation for is to talk about the binomial coefficient. Let me actually start by working through a specific example first, and then we'll do the general case. Suppose we wanted to calculate 4 choose 2 using exponentiation and polynomial things. First, we'll calculate 11 to the 4th. This is 14641, the 4th row of Pascal's triangle. Next, we'll need to extract the hundredths digit of this number here. And we can do that by writing 14641 as the sum of everything to the left of the hundredths digit, so some x times 1,000, plus our hundredths digit times 100, plus something less than 100. There's only one way to break 14641 apart like this, with y less than 10 and z less than 100, and that's x equals 14, y equals 6, and z equals 41, and y here is our hundredths digit. And we can generalize this sort of process to work out any binomial coefficient we want, but we need to be a little bit careful. The binomial theorem gives us this sum here. And as long as we pick a base b that's large enough that there's no carrying when we do this sum, the b to the kth digit of b plus 1 to the n in base b is the binomial coefficient n choose k that we're looking for. And again, it's really important to pick a large enough base b. If we try to use the technique of looking at powers of 11, to work out larger binomial coefficients, it wouldn't work because there'd be some carrying when we went to take 11 to the 5th, for instance. So in order to calculate n choose k, we first need to begin with a large enough base, and b equals 2 to the n plus 1 will do. And then we write 1 plus b to the n as some stuff before the b to the kth digit, plus the b to the kth digit, plus the stuff after the b to the kth digit, with again y being some actual digit in base b, and z being strictly less than b to the k. And so if we have an equation in our system of equations like y equals n choose k, we can rewrite it as the following system, which we can eventually translate using our translation procedures down to a system of polynomial equations and a single polynomial equation. Now, of course, I promised programming with Diophantine equations. And in order to do that, we're going to need to use our numbers to represent data in a binary format. A useful relation for talking about the binary representation of numbers is the binary subset relation. Given two natural numbers, we say that x is a subset of y, which we denote with this triangle less than or equal to sign, if the positions of ones in the binary representation of x are a subset of the positions of ones in the binary expansion of y. I've plotted out a diagram of this relation for the two-digit binary numbers 0 through 3. Each column corresponds to a different x value, reading from left to right, from 0 to 3, which shows up as the top number in each cell, and each row corresponds to a different y value, reading top to bottom from 0 to 3, which shows up as the bottom number in each cell. And I've highlighted each cell where the x-coordinate is a binary subset of the y-coordinate. For instance, this cell here is highlighted because the binary digits of 2, that is 1, 0, form a subset of the binary digits of 3, that is 1, 1. If we plot out larger versions of this sort of diagram, we can see a pattern start to emerge. Here, I've plotted out all of the pairs of 3-digit binary numbers. Again, the x-coordinate is the top number, and these go from 0 to 7 across the cells, reading from left to right, and the y-coordinate is the bottom number, and these go from 0 to 7, reading from top to bottom. And we're going to unhighlight the pairs where the binary digits of x are not a subset of the binary digits of y. Starting with the leftmost digit, I've unhighlighted the pairs where the first digit of x is 1, but the first digit of y is 0, and thus x is not a subset of y. And we notice that this divides the region into quarters and removes the top right quarter. Next, let's unhighlight pairs where the second digit of x is 1, but the second digit of y is 0. Again, making x not be a subset of y. This removes the top right quarter of each of the remaining quarters. It would also remove the top right quarter of the top right quarter, but we've already removed that. And finally, let's unhighlight pairs where the third digit of x is 1, but the third digit of y is 0. These are the top right quarters of each of the tiny boxes we had before, the quarters of quarters, and the result is a shape that might look familiar. It's a discrete approximation of the Sierpinski triangle. This is even clearer if we look at the 4-digit binary numbers. That same removal process leaves us with this particular triangle here. This discrete Sierpinski triangle shows up in Pascal's triangle. If we highlight the cells with odd numbers in them, we get the same pattern. This gives us the following lemma. X is a subset of y if and only if y choose x, the corresponding entry of Pascal's triangle, is odd. And of course, since we can express y choose x and is odd using Diophantine equations, we can also express x being a subset of y using Diophantine equations. Here's that same diagram for the first 16 rows of Pascal's triangle. This is a special case of what's known as Lucas' theorem. Given a prime number p, we can work out the remainder of m choose n modulo p by taking the product of the binomial coefficients formed by the respective digits of m and n in base p. You can prove this by induction on the number of digits of m and n in a way quite similar to the visual proof that I just presented. Using our base 2 subset relation, we can describe a bitwise AND and a bitwise OR operation. The idea here is that we'll again be thinking of our numbers as sequences of digits in base 2, and the bitwise AND operation gives us a number with 1s where both inputs have 1s. And the bitwise OR operation gives us a number with 1s where either input has a 1. So notice that the bitwise OR operation gives us a number that's larger than both of our inputs, and the bitwise AND gives us a number that's smaller than both of our inputs. The bitwise AND and bitwise OR are characterized by the following. The bitwise AND is a bitwise subset of each of the inputs, and the bitwise OR is a bitwise superset of each of the inputs. And also the sum of the inputs is the sum of the bitwise AND the bitwise OR. This is easy to see once you note that the number of 1s in each column in the top half of our example is the same as the number of 1s in each column in the bottom half. Right, in this column there are 2 1s both up here and down here, while in this column there's 1 1 here, and in this column there are 0 1s here and here. And this is an exact characterization. If these 3 conditions hold, then C is the bitwise AND of A and B, and D is the bitwise OR of A and B. To see this, we first rewrite our third condition as A minus C equals D minus B. Note that because C is a binary subset of A, the subtraction A minus C doesn't involve any borrowing. It just gives us a number with 1s in positions where A contains a 1 and C does not. Similarly, D minus B gives us a number with 1s in positions where D contains a 1 and B does not. Since these numbers have to be equal, these sets of positions have to be the same. Similarly, we can rewrite our equation a different way to get that the positions where D contains a 1 but A doesn't are the same as positions where B contains a 1 but C doesn't. Together with the fact that C is a bitwise subset of D, it's very straightforward at this point to prove that C and D are the bitwise and bitwise OR that we wanted them to be. And of course, bitwise negation is just subtraction from a number which is all 1s in binary. That is 2 to the n minus 1 for some suitably large n. And we can ensure that n is large enough using an inequality. We now have all the tools we need to describe one-dimensional cellular automata. If you've ever heard of Conway's Game of Life, this is similar, but based on a one-dimensional grid instead of a two-dimensional grid. So let's imagine we have a one-dimensional grid, a tape of 0s and 1s evolving over time, and we have a rule for determining what goes in a particular cell at time t based on what was in that cell and its neighbors at time t minus 1. At the top, I have the 8 rules describing a particular cellular automaton. For instance, this rule highlighted here says that if we're looking at a cell and the cell to the left has a 1 in it, the cell itself has a 1 in it, and the cell to the right has a 0, then we look to the bottom of the T to see what the cell should be at the next instance. And in this case, the cell should still have a 1 in it. Below these rules, I'm going to write out a tape that has 0s and 1s in some sort of random starting configuration. And I'm going to write out below what the tape looks like at the next instant of time. The first cell becomes a 1 because the cell to the left is considered a 0 because it's off the end of the tape. The cell itself is a 0, and the cell to the right is a 1. And we look this up on our rules, and that tells us that the cell should become the number at the bottom of the boxed T. For the second cell of the tape, the cell to the left was 0, the cell itself was 1, and the cell to the right was 1, so the cell remains a 1. For the third cell, its neighborhood reads 110, so the cell should remain a 1. For the fourth cell, its neighborhood reads 101, and so that 0 should become a 1. And so on and so forth. And again, we consider cells off the end of the tape as being 0s, so here we look up 010, so the last cell should remain a 1. So this is what the tape looks like. This second row here is what the tape looks like at the second instance of time, at the second step. And we continue this process again, and again, and again, and again. And it causes the sequence of cells that we have on the tape to evolve over time. So this is a one-dimensional cellular automaton. Sometimes you'll want to consider it as taking place on an infinite tape. Sometimes you'll want to consider it taking place on a finite tape. And depending on our choice of rules, we'll see different patterns emerge. Suppose that we wanted to express that this particular sequence of tape configurations here follows this cellular automaton rule. First, I'm going to represent this sequence as a single number x, written out here in binary. Here I'm just concatenating all of the rows together, again in binary, and again I want a Diophantine condition on x to tell us if it's in fact a sequence of steps according to the cellular automaton. To do this, we're going to want to be able to compare each of our rows in x with the row above. We can get this by dividing x by 2 to the 6th, 2 to the number of cells in each row, so that 6 is actually going to be a variable that represents the number of cells in each row. And we have to round down since everything is an integer. So here, for instance, we're comparing row 2 in x, 0, 0, 0, 1, 1, 0, with row 1 in x divided by 2 to the 6th, 0, 0, 0, 0, 1, 0. Lining these numbers up like this allows us to use our bitwise operations, bitwise relations, to compare the cells in one row with the corresponding cells in the previous row. And we need to compare our rows in X not just with the corresponding cells in the previous row, but also their neighbors, which we get by shifting over one bit, that is either multiplying or dividing by 2. So now each column here corresponds to a T shape in the original diagram. For instance, this column here corresponds to this T here. So if we use modular arithmetic to cut off the first row in X, we just need to assert that each column we have here is one of our T's, which we can do with our bitwise operations. Every bitwise operation is generated by and, or, and not, and every bitwise relation is generated when we toss in equality as well. Now, I've specifically chosen an example where wrapping around the edges doesn't make a difference. This column here actually corresponds to these cells here, and we want it to correspond to these cells with an extra 0 here since we're off the end of the tape. Luckily, we can look at numbers like this to detect the ends of the column and toss that into our Boolean conditions. This might be an avenue for completing the proof that Diophantine equations are Turing complete directly. This particular rule for a one-dimensional cellular automaton is known to be Turing complete in particular circumstances, but I don't understand that proof well enough to use it directly. But in fact, we can just use our ability to talk about cellular automata to talk about Turing machines. Normally we represent Turing machines as having some tape with a read-write head in some location and some state associated to the read-write head. But all we have to do is incorporate the state into the symbol at the location of the read-write head, and we have a one-dimensional cellular automaton. The future symbol of a cell is determined by the symbol of that cell and its neighbors. Specifically, if a cell has the read-write head, then its future symbol is determined by the operation of the Turing machine. And if a cell is next to the one with the read-write head, then it might wind up having its symbol change depending on that neighbor's symbol, depending on if the head is going to move left or right into the cell that we're currently considering. Of course, this sort of cellular automaton has more than just two symbols, more than just 0 and 1, and we've only seen how to work with cellular automata with just two symbols. But this is really straightforward. Let's say for simplicity that we want to work with a cellular automaton with just 3 symbols, A, B, and C, and you can use this process to work with cellular automata with any number of symbols. We can represent the tape then as 3 values, A, B, and C, which in their binary representations have 1s in positions where that character is. Then we have to say that A, B, and C together partition some number that's all 1s in binary, which we can do using bitwise subset. And then we have to shift all 3 of these, like we did with X on the previous slide, and throw them all into a giant Boolean relation describing the transition rules of the one-dimensional cellular automaton. One objection you might have is that so far I've just been talking about finite tapes, when Turing machines are allowed infinite tapes and infinite time. But actually, any Turing machine that actually does halt, any Turing machine that outputs some value from a computation, only uses some finite amount of tape and finitely many steps. We don't know what that finite amount is, and we certainly can't cap it from the start without having a finite state automaton. What we're really saying here is that there exists some finite tape length and some finite number of steps, and some number or numbers containing all of the data for the sequence of steps of the computation satisfying our Boolean conditions that we came up with. And that's exactly what's going on with Diophantine equations, right? There exists some variables, some natural numbers, satisfying some conditions. And then you might ask, how exactly can we figure out what the starting and ending configurations of the tape are, given one of these numbers or sets of numbers describing the tape? And how can we make sure that the final configuration is the first occurrence of a halting state? All in all, there's lots of fiddly details one needs to work out, and one can work out. But this video is about practical programming of Diophantine equations, so let's look at a more practical abstraction of computation than Turing machines. Specifically, I'd like to look at a specific type of register machines. These are also sometimes called counter machines. I made a separate video which I'll link down below where I prove that register machines are Turing complete and show you how to do some basic programming with them. But just to remind you, a register machine has a finite number of registers that each store arbitrary natural numbers and a finite list of instructions in some sort of assembly-like programming language describing the operation of the machine. These instructions can be one of increment one of the registers, that is, add 1 to its value, decrement one of the registers, that is, subtract 1 from its value, unless it's already 0, in which case we do nothing, jump to a different line of code, do a conditional jump. If a register is empty, if it contains a 0, then jump to a particular line of code, and if not, just move on to the next line of code. The various sources for the proof that register machines are Diophantine that I've been working from require that you use this instruction to avoid decrementing a register that already has 0 in it, just to make the proof easier. And that's not a big deal. You can easily modify a program that doesn't have that to make that happen. And finally, we have a halt instruction. Again, the proofs I'm working from make a few simplifications to make the proof easier. For instance, they require that only the last instruction be a halt instruction, and that all registers be empty except possibly whatever output we want to output when we do halt. So here I have an example setup for a register machine. At the top, I have two registers, R0 and R1, and we'll start off with a 2 in R0 and a 0 in R1. The convention is that at the beginning of the program, all of the registers start off with zeros in them, except for any registers that we're using as inputs. So we're kind of thinking of this as inputting a 2 into this machine, and we'll see what number we get out. And then I have the program. This program loops around between lines 0 and 4, subtracting 1 from R0 and adding 2 to R1 until R0 is empty. So when it's done, we will have twice the initial value from R0 now in R1, and R0 will be empty. So we could say that this program calculates the doubling function. Let's watch the program in action, and as we go, I'm going to keep track of some information over to the side. So at this first step, our registers read 2 and 0, and we'll jot that down on the right in variables R0 and R1, and we're looking at line 0 in our code. We always start at line 0, that's the convention, so I'm going to write a 1 in the variable L0 and zeros in the variables for the other lines of code. So these L's, each L corresponds to one of our lines of code. We're going to put 1s to tell us which line of code we were executing. Looking at our code, register R0 doesn't contain a 0, it contains a 2. So instead of jumping to line 5, we'll just move on to the next line. When we get to this next line, the registers still read 2 and 0, so we'll prepend, that is, add on to the beginning, a 2 and a 0 to our R0 and R1 variables on the right, and then we'll prepend a 1 to the left of our L1 value to indicate that we're now at line 1 in our code, and we'll prepend a 0 to the other L variables. Of course, when we read that decrement code, it will subtract 1 from R0, so at the next step, R0 is going to have a 1 in it. And this is fences or fence posts as to whether or not the decrement R0 instruction being on line 1 means that you want to decrement going into line 1 or coming out of line 1. But the convention in the proofs that I'm working from is that you should decrement coming out of the decrement line. So again, we're going to prepend those values. 1 and 0 to R0 and R1, because those are the new values in the registers. And we'll add a 1 onto the left side of L2 to indicate that we're at line 2 of our code right now. And of course, just like with decrement, increment, coming out of line 2, we're going to want to increment the register R1. So again, after we've incremented R1, we now have the value 1 in that register. So that changes what we prepend to the variable R1 on the right. And now notice that L3 starts with 1 because we're at line 3. And then we keep going. Notice how the execution loops around when we reach line 4, so now we're back with a 1 being prepended to our value L0. And we go through the loop again, and now R0 is equal to 0, so we jump to line 5, where we halt. So that was our execution of our code. The double of 2 is 4, and a complete trace of the execution of our code is contained in these strings to the right. And now I'm going to show you how we can translate this program into a Diophantine relation. Our program calculates some f, and so we're going to say that f of x is equal to y if there exists some other variables, z, w, whatever, such that all of these variables satisfy some polynomial equations. Now, it just so happens in this example that that function is the doubling function, and this is pretty easy. But I'll go through a translation process that will be general, so you can translate any computable function you want into a corresponding system of polynomials. Now, very sensibly, our r's and l's on the right are going to be some of our other auxiliary variables. Specifically, we're going to want to pick some base b, and these will be the digits of some numbers in base b. And we can't pick b in advance. We need b to be one of our variables that we quantify over. We say there's some base b satisfying a bunch of conditions making this all work out. First, I'm going to want b to be a power of 2 so we can use our bitwise subset relation. Next, we're going to want b to be large enough that none of the numbers we want to be digits in base b exceed b. Specifically, the values in all of the registers at any time have to be less than b. And for a trick that we're going to do later on, we're actually going to want b to be at least twice the largest value occurring in a register. And we'll ensure that this happens by having a separate variable s, and that's going to represent the number of steps of the computation. And again, x is our input. And so the largest possible value we could get in a register, if we have a program, the input is x, and it takes s steps, we could just increment that particular register at every step. And so the largest value we could get is x plus s. And so again, we're going to require b to be at least twice that. We'll also want b to be at least the number of lines of code just to make something a little bit easier later on. Now, let's start coming up with some conditions on the Ri and Li to force them to represent a valid execution of our program. First, we're going to want to require that the Li form a partition. In each place, exactly one of them has a 1 and the rest have zeros. And this is up to length s, the number of steps of our computation. To do this, I'm going to introduce a value I, which is a sequence of s1s when written out in base b. And that's just b to the s plus 1 minus 1 divided by b minus 1. And of course we can translate this into a Diophantine condition by multiplying both sides by b minus 1 and unpacking the exponent. So now requiring that the Li form a partition is just requiring that their sum is I, and each is a bitwise subset of I. Again, we're working in a base that's a power of 2, so that the bitwise subset relation on numbers written out in base b is just going to check that each digit of one number is a bitwise subset of the corresponding digit of the other. And of course, the only way to be a bitwise subset of 1, remember that I is just all 1s, is to be either 0 or 1. So saying that Li is a bitwise subset of I is going to require all of the digits of Li in base b to either be 0s or 1s. And this here is also why we want the base b to be at least the number of lines of code, so we can very easily say that together the union of L0 through L5 gives us all of I just by saying that their sum is I. And because b is at least 6, there can't be anything tricky going on with carrying when we do this sum. This isn't necessary. You can describe partitions just using bitwise operations, bitwise relations, but this is a really elegant way of doing it, and all it requires is that b be at least 6. So that's fine. Next, we're going to require that we start at line 0. The ones digit of L0 in base B must be 1. Again, when we're talking about bitwise subsets in base B, we're just checking if each digit is a bitwise subset of the corresponding digit in the other number. So here we're checking that the number that's, all zeros followed by a 1 is a bitwise subset of L0. That is that L0 in its ones place has a 1. And of course we want to allow L0 to have ones elsewhere, which is why we're using a subset and not an equals. Then we require that we reach the halt line at the last step and no earlier. L5, on the other hand, has to be exactly b to the s. And now comes the tricky part, making sure that the transitions work out correctly. Some for all quantifiers would be really handy here. We could use them to say, for instance, that for everywhere there's a 1 in L1, there's a 1 in L2 the next place over, to indicate that we always transition from line 1 to line 2. And when this happens, that the value in R0 decrements between those places. But that's exactly what we don't have when we're working with Diophantine equations, universal quantifiers. Let's start with the simplest line, the goto. We want to make sure that if there's a 1 in the b to the ith place in L4, then there's a 1 in the b to the I plus first place of L0. We do this by requiring that b times L4 is a binary subset of L0. Right, b times L4 is going to have ones right after, that is to the left of positions where L4 has ones, and in these positions we definitely need to be in L0. There might be other ways of getting to line 0. Specifically at the beginning we started at line 0. So we just require that b times L4 be a subset of L0, and this not be an equality. Now let's try to come up with some Diophantine conditions constraining our representations of the registers. Here's what the contents of register 0 look like. Again, we're representing the sequence of values from each step from right to left, and this is a number in base B. The key thing we're going to do is compare R0 with B times R0, the same sequence but shifted over one step. Now, for the most part, these are going to agree with each other. The value in register R0 by default doesn't change from one step to the next. But there are a few things that can change it, and to see where these changes happen, we just need to subtract R0 from BR0. But notice that if we do that subtraction now, the ones digits are going to borrow, and that's going to throw everything off. So I'm actually going to toss in the starting value for R0, so the subtraction works out nicely. Recall that we're representing the input to our computation as x, and for our particular example, we inputted a 2 into our function in hopes of doubling it. Now we can subtract these two lines from each other, and we get this, a representation of the lines where we decremented register 0. That happened in our code on line 1, and here's our variable representing when we were on line 1. These are off by a step, but otherwise agree. So all in all, this difference that we got must be equal to b times L1. This equation here, once we've determined b, L1, and x, is enough to force R0 to be the sequence that it is. Now let's look at our sequence for R1. Again, we're going to want to compare this with what we get when we offset by a step. And again, we're almost set up to do a subtraction, but now we're going to need to add an extra 4 onto the beginning of R1 to have any hopes of subtracting properly. That is, we're adding y, the output of our function, times b to the s plus 1. Remember that s was our number of steps. So now we can subtract and we get this, which this time captures the positions where we incremented R1. Looking at the lines, line 2 and line 3, where we did this, again we need to offset by a step by multiplying by b, giving us this equation here. Our difference that we computed is going to be b times the sum of the lines where we incremented R1. These are specific examples, but they show off all of the pieces we might have to work with for each register, incrementing, decrementing, and dealing with inputs and outputs. Although in general, we should be prepared for certain registers to be both incremented and decremented. In general, the equation that we're going to want to set up for a particular register looks like this here. The difference between the offset version of Ri and the original is given by b times the sum of the line number variables, the positions where we decrement Ri, minus b times the sum of the line number variables where we increment Ri, minus xi if we're going to treat register I as an input to our machine, otherwise just leave that as 0, plus yi times b to the s plus 1 if we're going to treat register I as an output to the machine. Otherwise, just leave that as 0. And we're going to want to set up one of these sorts of equations for each register, and these will fully describe the behavior of all of the Ri. So let's add these equations onto our specification. And we're also going to need to add on a requirement for each of our increment and decrement operations that after them, we go on to the next line. And these are just like the go-to conditions. Right? It's kind of like increment and then go to the next line. All that's left for us to do is to figure out how to translate our conditional jump into a Diophantine constraint. Here we have our line of code and the relevant variables. Specifically, if we're at line 0, we're interested in either transferring to line 1 or line 5, depending on if R0 is empty or not. So our variables L1 and L5 are both going to be relevant here. To get started, we can specify that the step after we're at L0, we're definitely at one of L1 or L5, with this inequality here. If we shift our L0 over one place to the left, it lines up with the ones in L1 and L5. And again, just like in the go-to case, this is going to be an inequality and not an equality, since there might be other ways of getting to lines 1 or 5. For this particular program, there weren't, and we can see that these are equal looking at L0, L1, and L5 here. But generally, you're going to want to translate conditional jumps with an inequality to allow for other ways of getting to the target lines. But in order to fully constrain our conditional jump, we need to be able to determine which of L1 or L5 we're going to jump to. Specifically, we'd like some sort of sequence, some number in base B that has a 1 where R0 is 0 and a 0 where R0 has a number larger than 0, so that we can do some Boolean stuff to it. In order to do this, I'm actually going to want to look at the base 2 composition of our values. To the left, everything is written out in base B, even the Li, although they just consist of zeros and ones. That's zeros and ones, but in base B. To the right, I'm going to write everything out in binary. For simplicity, I'm going to assume that B is 8, that every one digit on the left corresponds to 3 digits on the right. This actually can't be the case, of course. Our constraints require B to be a power of 2 that's at least twice the largest input plus the number of steps. So it has to be like at least 32, but it's going to be easier to draw everything out and fit everything on the slides if we let B be as small as possible. And again, the important thing about our choice of B is that B be at least twice the largest value occurring in the register. So B equals 8 is a good choice to see what's going on, but it's not really accurate to what happens when we're solving our giant system. And I'm actually going to want to bring in our I value from before, chosen to be the appropriate length and all ones in base B. Each of those ones is going to correspond to a 0, 0, 1, Again, we're in base 8 in binary. And actually, I'm going to want to look at b over 2 times I. In base b, this number is going to be all b over 2's. And for our improper choice of b being 8, this is going to be a number that's all 4's, or 100's in binary. And again, we deliberately chose our b so that b over 2 is larger than any value we could have in the register R0, any digit that we could have when we write our R0 in base b. So if you look on the left, it's clear that we can subtract R0 from b over 2 times I in base b without any borrowing. And that's the real trick. I'm going to copy down R0 below on the right so that we can take a closer look at what happens when we subtract in binary. First of all, we deliberately chose our base b to be at least twice the largest possible value ever appearing in a register. Put another way, when we look at our register R0, these digits specifically are always going to be 0. And again, this is going to be so that when we subtract R0 from b over 2 times I, each of these groups of 3, each of these digits in base b, doesn't have to borrow from the next group of 3 over. There might be borrowing within the groups of 3. There might be borrowing in the binary subtraction, but there's not going to be borrowing between these groups of 3, between the digits in base b, in base 8. So when we do this subtraction, if we look closely at these bits here, they're exactly what we're looking for. In places where R0 was 0, the 4 stayed as it was, leaving a 1 in these bits here. Right? If you look to the left, when we did the subtraction, the 4's, we're subtracting 0 from them, so they stay as 4's. And on the right, that looks like 100. On the other hand, in places where R0 was larger than 0, we subtracted a positive number from the 4, getting rid of that bit. So again, on the left, when we look at the columns where R0 is larger than 0, when we do that subtraction, we're going to get numbers like 3 and 2. And those numbers, when we expand them out in binary, are going to look like 011 and 010. And so that leading digit is going to be a 0. So again, that leading digit there tells us it's going to be a 1 in positions where R0 is a 0. It's going to be a 0 in positions where R0 is larger than 1. So now all we have to do is use some Boolean logic to extract these bits and compare them with the locations where we transition from line 0 to line 1 versus line 5. This sort of Boolean logic can get a little bit gross, especially if we're trying to combine a lot of Boolean operations together, but the papers that I'm looking at for this proof actually suggest a very slick way of extracting these values and using them to constrain the L0, L1, and L5. And what they do is they actually look at twice this value here, and that it just shifts over 1 unit when we're looking at things in binary. And then we try to add it to L1, and the result should contain all of the 1's of BL0, which we'll write as this inequality here. Specifically, in places where L1 does have a 1, we want the corresponding value in R0 to be positive. We want the orange bits to be 0's. And this enforces that, because if there was a 1 in the orange bits, we'd get a carrying, and the resulting bit of the sum would be 0. On the other hand, in places where L1 does not have a 1, but we were in L0, so places where L1 does not have a 1, but B times L0 does have a 1, we need a 1 from the orange bits to pick up the slack. So that's a very clever way of describing this constraint here. But again, the important part was that we have a way of detecting when R0 is empty, so we can just use bitwise logic. This is just a clever trick from the proof that avoids having to do too much bitwise logic. Looking back at our sample program, this gives us our final set of conditions. And again, this is a set of conditions describing a Diophantine relation between x and y that holds when y is the output of our program given x as input, and specifically when y is twice x. And again, this is silly for this case, for this program, but we could translate any program we like, any computer program that takes in a fixed size tuple of natural numbers and outputs a fixed size tuple of natural numbers. We can translate an arbitrary computer program into a register machine program, and then translate that to a Diophantine system of equations using exactly the same technique. So any computable function is going to be a Diophantine function. And vice versa, any Diophantine function, we can compute it. That's pretty straightforward. You just hunt for solutions to your Diophantine system, and as long as you know they're out there, it's perfectly fine. I want to take a moment to talk about what happens if we try to translate a program that doesn't halt. There are plenty of reasons why a computer program might not halt. Maybe we detect some condition happening and deliberately jump into an infinite loop. Or maybe we're hunting for something that doesn't exist, but we don't know doesn't exist. And if these programs have inputs, whether or not they halt can depend on the input. We can, of course, take these programs and translate them into register machine programs with the same status of not halting, or maybe conditionally not halting, depending on the input, using some sort of straightforward compilation process, depending on what our original programming language was. And then we can translate these register machine programs into Diophantine equations. Part of those Diophantine equations is saying that there exist L's and R's tracing out the sequence of states of our register machines, starting in this particular way, ending in this particular way. But of course, such L's and R's can't possibly exist because they would then have only finitely many digits to them, and thus give us a finite sequence of steps in accordance with the operation of our machine from the start to the end. And we said our machine doesn't halt when we run it according to its operation. So not halting corresponds to there not being a solution to our Diophantine system of equations. And this makes sense, of course. If we wrote a naive Diophantine equation solver that just brute force tried all tuples until it found a solution, there not being a solution would correspond to our program not halting. Unfortunately, there is no algorithm for determining if a computer program halts that works correctly in all cases. Sure, you can sometimes detect infinite loops, but it can't be done in general. And, well, if we had an algorithm for solving Diophantine equations, or even just determining if a Diophantine equation had a solution, we could use it to build one of these impossible halting algorithms. Just translate your program to a Diophantine equation and ask if it has any solutions. So, contradiction. We can't have an algorithm for determining if Diophantine equations have solutions. So that's all I wanted to cover in this video, but there's plenty more to say about Diophantine equations and the negative result to Hilbert's 10th problem, which I'll save for the future. In the meantime, let me know if you have any questions or comments below, and be kind to each other.